All right, section 2.2, the derivative function. So in this section, we're going to get more practice dealing with graphs and understanding the derivative in terms of its graph, and being able to tell something, to read off information about the derivative given the graph of a function, and being able to see what the graph of the derivative would actually look like. Okay, so if you're still holding on to some idea that at some point you can just forget about graphs because you don't like graphs, I'm hoping to squash that hope completely this section. So graphs, very important. We need them. They're very helpful. They even made there's a quote somewhere, a saying somewhere, a picture. It's worth I don't know. I can't remember the exact saying. A picture's worth a handful of a bunch of words or something like that. I don't know, but it's worth a lot of words. So keep in mind, picture. It's very helpful, not just formulas. Let's get started. So last time, what did we do? We introduced the idea of the derivative, which is the slope at a particular point, not between 2 points, but actually at a point. And we have a way of calculating what that is. Given a point, we'll find the average rate of change between the 2 points, and we'll just make the 2 points get very, very close to the point that we're actually interested in. All right, and the subtle point here is that given a function f of x, if we do this process for each x coordinate, we get another function. Each x coordinate corresponds to a slope at that x coordinate. That's what f prime of x represents. That's what, oh my gosh, it's highlighting everything that I touch. Okay, that's what f prime of x represents. It's called the derivative. It represents the slope at the point x. Okay, and what do you think we're going to do? We're going to look at the picture. We're going to look at the picture because we want to know, we want an idea of what we just found. It's all great finding those formulas, but we really need to look at a picture to understand what's going on here. So remember, I put this in the last video. We have e to the x here, and if we draw the tangent line, there's only one of them. If we draw that tangent line, the line that grazes the curve at only 1 point at x equals 1, and we find the slope of that line, that's the derivative. All right, that's how we do it. Okay, so the derivative at x equals 1, that's the slope of the tangent line at x equals 1. Okay, so that's that. All right, now, we don't normally address this kind of question in math very often. Why do we care? And it's not that we never address it, but it just doesn't seem necessary to constantly worry about this question, because what happens when you work more math is you just naturally see its relevance. You naturally see how it can be useful for certain things, for understanding this world, understanding relationships and patterns between things, predicting things. Okay, but let's take a moment here, because we just did a lot of stuff, and there's a teachable moment how this stuff can be useful. Now, it requires a little bit of imagination on your part. This is a slightly abstract example. But suppose that we had information about profit in, say, our company, the profit that our company was making for producing a certain amount of items. And suppose that we only had 1 point of information. We only knew that that we were losing money, that our profit was negative for producing a certain point. Then we might think, oh, bad, we're losing money. But if we knew that the function was increasing at that point, meaning that as we increased production, that profit actually increased as well, then later on we would realize, oh, actually, if we keep producing more though, we will make money. We will be in the positive, be in the green, right? Then we might think, oh, great, good, perfect. Well, if we're increasing production, we're making more profit, let's just keep making more and more and more. But then we might make too much. And then what happens? We go in the red again. Bad, bad, bad. Okay? So we don't have, this is not a world of perfect information. This is not an ideal world. We don't have all the information. But, and this requires a little bit of imagination on your part, but if we know what's happening very well for a small part of something that we're interested in, we can perhaps predict what will happen later. You see that? Okay. Well, that's the best I can do. I think that in working with this stuff, I think for most people, calculus students, they kind of get how it's useful just by working problems. They start to see, oh, okay, I kind of get how this could be useful. But if you didn't, or if you don't, maybe this helped a little bit. Anyways, so that's that. Let's move on. All right, so as we talked about before, if we have a function f of x, we can find the slope at each point, and what we get is another function. And if it's another function, it should have a graph, right? And so here's an example. I put two functions right on top of each other so you could see how they line up. They should line up. What should this tell us? Well, we have a function here. What should the derivative tell us? Remember, the derivative tells us information about how the function is changing. How's the function changing over here? It's decreasing. It's decreasing. It's going down. That should mean that our slope is negative. Slope is negative. Well, if we look at our derivative function here, for these x coordinates over here, we have a negative derivative. In decreasing function, negative derivative. Over here, the function is increasing. If the function is increasing, that should mean that our slopes are positive, which they are. They're above the x-axis. And how about at this point here? The function at this point has stopped decreasing and has not yet begun to increase. So the slope at this point is 0. And when we notice, as we go to our derivative, and it is 0 at that point. Right? So these things should line up. They should line up. Should correspond like that. Right? Decreasing function means the slope is negative. Increasing function, slope is positive. Function staying the same, slope is 0. That wouldn't fit on the slide. All right, another picture. So we haven't talked about this yet, but we will very soon, as in like the next section or something, that the second derivative. So you could do this process again and again. You could look at how a function is changing. Okay, that's the derivative. Maybe I want to go again. How the derivative is changing. That would be the second derivative. And I could go again, and so forth, and so forth. But usually we stop at this point. We stop at the second derivative. All right. Each time we take the derivative, that tells us how the previous function is changing. It will turn out that the second derivative tells us about the concavity of this function here. We will talk about that later. Very soon. All right, in your Wiley plus, why do they both have to start with a W? In your Wiley plus, you're asked questions like this. Given a function f of x, which candidate could reasonably be its derivative? So let's see, if we're trying to find a graph of the derivative, that should tell us how the function is changing. Well, we should know how the function is changing. First of all, it's increasing over here. It's also increasing over here from left to right, and it stops at this point. So the slope is 0. So we would expect the derivative to be positive over here, and 0 here. let's see, does B fit that description? B is negative over here. That means that should mean that f of x is decreasing for these x values, but it's not. It's increasing. And B also says that function f should be decreasing over here, but it's not. It's increasing. It's increasing. So not B, not B. How about C? C says that over here it's increasing because we have a positive derivative. Okay, that seems plausible, because f of x is increasing. And C says for these x values, for these positive x values, the function f should be decreasing because we have a negative slope, because the slope lies below the x-axis. That doesn't fit f of x because f of x is increasing over here. So we should have a positive graph over here, which we don't. It's down here. So it's not B or C. So what should it be? Let me think. Oh, I forgot. We have A. Let's look at A. Is it A? Let's see. A. Let's see. We have a positive slope over here. Is f of x sloping positive? Yes. Is f of x increasing for positive x values? Yes, it is. Does f of x have a slope of 0 at x equals 0? Why, yes, it does. Yes, it does. All right, so A looks plausible, and that's the answer. Good. All right. And the last example for today, for now, is more on inflection points. Just one thing to add about inflection points. So we've talked about inflection points before, and we define them as points on the graph where the function changes concavity, or where the graph changes concavity, where it changes from up like a cup to down like a frown, or vice versa. Okay. And the point of this slide is to tell you that inflection points are, whenever you're asked to find points of most rapid increase or most rapid decrease. So not only are we concerned with is the function increasing or decreasing, but what's like a steepest point of increase or the steepest point of decrease. So this graph that I have here, the function is decreasing on this bit here, and where's it decreasing most? It's decreasing most at this point here. It becomes steepest at this point. It's going down by more and more, but then it goes down by less and less. It starts to level off slightly. So this point right here, that's the point of most rapid decrease, we say. Happens at inflection points. So keep that in mind. You might say, okay, well, what about over here? If we're talking about increasing, do we have an inflection point over here? Because it's pretty steep, it gets steeper and steeper. Yeah, but it doesn't reach a maximum steepness. It just keeps getting steeper and steeper. If it had an inflection point, it would start to level off like this. It would start to that steepness would start to decrease at some point. So we don't have a point of most rapid increase. Or maybe we would say, take the rightmost point if we were asked that, but usually you won't see something like that. Okay, that is all I have today. A lot lighter than the previous video, so hopefully stuff is starting to sink in a little bit, but this stuff is difficult, so it's understandable if it takes time. So give yourself time. Make sure to watch these videos as early as you can to give your brain time to process it before you have to do problems and stuff like that. Definitely don't want to wait till the last moment to do this stuff. But enough preaching. Have a good day, and I'll see you next time.